Now, what if we want to multiply add phases, right? We have to do that. So if we are applying two filters, and then we have to get the output of the filters, and then at the output of the filter, what essentially is happening is nothing but addition of phases, right? So we have to analyze that. So we need to know what happens when we add phases, when we multiply phases. So if you have two phases and then you multiply them, multiplication is very straightforward, like as good as multiplying complex numbers, which you already would know. So the magnitudes would just get multiplied as such. So this is equal to r times q. And what happened to the phases? The phases get added up. In other words, you can represent phases in this complex plane, real and imaginary part. So if I had something like this, let's say this is a phasor, this is r e power j omega t. It means that this distance is r and this angle is omega t. Okay, of course this angle is changing with time. Because it is changing with time, what would you see is, you would see that at time t is equal to 0, the phasor would be here. At time t is equal to 1, it will be here, and then it will keep rotating. It will keep rotating in the anti-clockwise direction. We'll see this in a little while. Okay, so we can represent the phasor here. If we have another phasor, let's say we have another phasor here, let's call that q e power j v t. The multiplication of these two is nothing but the magnitude gets multiplied and the phases get added up. So this is q times r, and this angle is omega t plus v of t. Okay. All right. So this is as good as a simple complex number multiplication in the case of product of phasors. Now, what if we want to add up or subtract phasors? Okay. This is not as easy as just multiplying phasors. So what happens to the magnitude first? So the way to approach this is to use the simple parallelogram law, where you have two vectors, like let's say this is r e power j omega t and this is q e power j. Okay, now we have two vectors. The resultant, or the sum of these two phasors, is basically nothing but the diagonal of this parallelogram that is constructed using these two phasors or these two vectors. Now, what would be this diagonal? This is the vector sum. So, how do you compute the vector sum? So, it depends upon the angle between these two, right? So, if this is a vector and this is a vector, now you compute this by finding out the length of the diagonal of this triangle, right? So, this triangle has the same length as q e power j omega t. So, you just move this vector on this side so that you construct a triangle, and the side connecting these two vectors is nothing but the resultant vector, and the length of that is given by the length of this side. In other words, you can compute that to be just, you can write this as r cos omega t plus j sin omega t plus q cos omega t plus j sin omega t. Now you have this to be the real part and this to be the imaginary part. So in order to compute the magnitude, all you have to do is just take the square root of the real part squared plus the imaginary part squared. That's exactly what you have to do here, and if you do that, you will get this particular expression. Okay, and as you can note here, if both are of the same frequency, what happens? So if both are of the same frequency, then this component, this value becomes 0, and cos of that is 1, and this entire thing is nothing but r plus q the whole square, which gives you just r plus q. So the magnitudes get added up if they are of the same frequency, right? In other words, what we are saying is it's just r e power j omega t plus q e power j omega t. So if w is equal to v, which means it's the same frequency and same phase. So it's just as good as saying r plus q e power j omega t. Right. So what is the phase if they are different? So once again, you can use the same thing here. You have to take the imaginary part and put it in the numerator, take the real part, find their ratio. So this is a very useful tool to analyze what happens in a circuit when there are a lot of capacitors and inductors, and then you are adding signals from, let's say, two capacitors or two different circuits. Then are they adding up in phase, or are they adding out of phase? If they are adding out of phase, what should you do? Should you include a component which will make them synchronized? So all these things you can analyze, and then you can modify your circuit and design the circuit only if you are able to analyze the phases at each and every component. And this phasor representation helps you to do this analysis. Okay, as you can see in this animation, that the horizontal component corresponds to cos omega t and the vertical component corresponds to sin omega t. Okay, and the phase is omega t. So when t is equal to 0, omega t is 0. When t is equal to 1, then the phase is omega. And then t is equal to, let's say, half, the phase is omega by 2. So which means as the time changes, the phase keeps changing. So because the phase keeps changing, the real value and the imaginary value also keeps changing. And as you can see, the magnitude remains the same, but the real value and imaginary value keeps changing. And if you plot, let's say, the imaginary value alone, you will get a sine function, and if you plot the real value alone, you will get the cos function. This you can clearly see in this animation. Now that is for a single phasor. Now what if you are adding two phasors? Let's take one phasor, which is denoted by this yellow line in this animation. So that's one phasor e power j omega t with some magnitude. Now if I have to add another phasor to it, how are we adding it? Let's say I'm adding another phasor of some smaller magnitude, which is represented by the green curve here. So I'm adding e power j omega t with e power j vt, let's say, where e power j vt is the green colored one, which is of a different magnitude. Now if I have to add this, the phasor's origin now goes on to the point representing the initial phasor. That is, the origin of e power j omega t was 0, but you are adding e power j vt to e power j omega t. So the origin has initially shifted to the location of the phasor e power j omega t. So wherever is the phasor e power j omega t, there you put the origin of e power j vt. And now both of these phases rotate together. When they rotate, you now find out where is this point that is present in the green circle moving. So this is now representing the sum of both the phasors. If you want to subtract, what do you do? Minus 1 could be written as simply e power j pi. So e power j pi is nothing but a phase shift. So the subtraction could be brought in as the phase shift. So instead of starting at 0, the green phasor will start at a phase of pi. So that will give you subtraction. Okay. So as you can see here, so if there is a first phasor that is starting at some point, and you want to add another phasor, you set this point, the first phasor's point, as the origin, and then start the next phasor from that. Okay, and then wherever is that phasor's location, that will be the sum of these two phasors. If you want to add another phasor on top of it, set that as the origin and then add another phasor. Okay, so if you want to subtract instead of add, do the same operation, but instead of starting at 0, you start at pi. Okay, so minus e power j omega t is equivalent to e power j omega t plus j pi. Okay, So subtracting two phases is simply nothing but adding them with a phase shift. Now you can notice one thing, all the phases are always moving in the clockwise, anti-clockwise direction. But what if a particular phasor is moving in the clockwise direction? What does it mean? This means we are getting a negative frequency. Okay. What does negative frequency mean? Now look at this animation. This animation gives you the same phasor but in 3 dimensions. As you can see here, this is a phasor which has a positive frequency, which means the rotation is in the anti-clockwise direction. Whenever the rotation is in the anti-clockwise direction, we say that the frequency is positive frequency. But whenever the rotation is in the clockwise direction, we say that it is a negative frequency. So what does it really mean to say that a particular complex signal has a negative frequency or the direction in which the phasor rotates? So remember earlier we said frequency is nothing but the rate of change of phase. If the phase is increasing, that is, it is starting at 0, the phase is starting at 0 and then it slowly increases to, let's say, 10, 20, pi by 2 and so on, it means the phase is increasing. The rate of change of phase is positive and hence the frequency is positive. But what if the phase is starting at 0 and then it is coming down, it is becoming -1, -2, -3 and so on, minus pi and so on, then the phase is reducing. So the rate of change of phase is negative, that is the derivative of this is negative. So that is what we refer to as the negative frequency. But as you can see, the real part, that is the horizontal component, remains the same no matter what is the sign of this frequency, which is basically cos of omega t, right? Cos of omega t is cos of minus omega t. That is the same. So the rate of change, it can either increase or decrease. The real part will not change. Only thing that will change is the imaginary part, because the sign of the vertical component will change. But what it represents is nothing but the direction of rotation. And where is this very useful is once again in our phase analysis. So negative frequency, it does not really mean that there is something which goes back in time. No, that's not the meaning of negative frequency. Negative frequency is only this direction of rotation of this phase. That is, does the phasor rotate in clockwise direction or anti-clockwise direction? Does the phase of the signal increase or decrease? So if we have two signals at the output of a filter, with respect to one output, the other output phase could have increased or it could have decreased. So in order to identify this increase or decrease, we are trying to use this phasor notation, and in this phasor notation, a negative component means the rate of change of phase is negative. So this is what it means to have a negative frequency. It's a mathematical quantity. Okay, it does not change anything in real life. The frequency in real life is always a positive number, but the negative frequency of the phasor, so whenever negative frequency is there, it is always that of a phasor. There is no negative frequency defined for a real valued sinusoid. The negative frequency makes sense only for a phasor, because only for a phasor we have rotation. For a real valued sinusoid, there is no rotation, right? So there is no sense to define negative frequency for real valued sinusoid. The negative frequency makes sense only in a phasor where there is a direction of rotation, and it says that if you move in this direction, then you get a particular rate of change of phase, and then you get a particular frequency which is either positive or negative, and the direction of rotation is either anti-clockwise or clockwise. Okay, and once again, the use of all this is to analyze what is the phase of the signals at the output of our circuits, filters, and so on. So given any complex valued signal, you can break that down into a real part, which is a real valued signal, plus j times another real valued signal. So this will together form the imaginary part, and this will be the real part of the signal. So the sum of two real valued signal, where one is multiplied with the complex number j, you get the complex valued signal. So in order to represent a complex valued signal, what you can do is you can plot the real valued plot separately and the imaginary. So earlier, if I had rectangular function, we just plotted just the amplitude of that with respect to time. But how would I visualize this complex signal? So what we can do is one way, plot the real part separately and the imaginary part separately. So this is one way of visualizing a complex valued signal. So in order to visualize a complex valued signal, you will need two plots. Okay, one is the real part and the other is the imaginary part. There is also another way to visualize the complex valued signal, that is plotting the magnitude and the phase, right? So either you can plot the real valued signal and the imaginary valued part separately, or you can plot the magnitude. Remember, the magnitude is always a non-negative value, and you can plot the phase of the signal with respect to time. So one thing that you have to keep in mind is when you try to compute the phase, you will just compute it as tan inverse of, x imaginary part of t by x real part of t. This is how you compute the phase, right? The phase is always going to be between minus pi and plus pi. So the phase is upper bounded by plus pi and lower bounded by minus pi. So whatever we'll get will be within this region. Okay, let's take an example and try and plot these things. So the general example that we had earlier was e power sigma plus j omega t. Now, what if the magnitude here r e power j omega t is what we had earlier, right? Now, what if this r itself was a function of t, and that is equal to e power sigma t? So that is what we have here. Okay, so this is an example of a complex signal. Now let's try and plot this and then observe what happens. So you can rewrite this as e power sigma t times e power j omega t. This is complex, this is real. So once again you can write this as e power sigma t times cos omega t plus j e power sigma t times sin omega t. The first plotting technique is to plot the real part separately and imaginary part separately. Let's do that. Let's plot the real part first. The real part is e power sigma t cos omega t. So how do we plot this? So we know cos omega t is nothing but just a sinusoid, right? Just goes on either side. What is e power sigma t? Let us first assume that sigma is less than 0. So if sigma is less than 0, we have e power some minus sigma t, where this minus denotes that sigma's value is less than 0. So it's a decaying function for this. So in this case, you'll have something like this. So what if sigma is greater than 0? Then we'll have e power sigma t. It's a growing function, right? So then it will grow something like this. Now, the real part is a multiplication of these two signals or these two signals. Now, let's see what happens when sigma is less than 1. If sigma is less than 1, we have something like this. If sigma is greater than 1, then we'll have something like this. Sigma is less than 0, sigma is greater than 0. Okay. Now, what about the imaginary part? It's the same thing, only thing that is different is Instead of cos, we have sine. So it starts at 0 or so this is sigma less than 0, sigma that is greater than 0. So this is a sinusoid, but the magnitude of the sinusoid keeps changing, and the sinusoid grows if sigma is greater than 0. The sinusoid decays if sigma is less than 0. Okay, so this is what we call as a growing sinusoid or a decaying sinusoid, and the sinusoid's magnitude depends completely on the sign of the sigma that we have here. So this is one nice example of a complex valued signal which actually might turn out to be very useful in analyzing circuits later. Now, if we have to plot its magnitude and phase, how does it look like? The same signal, let's take the same signal. Okay, what is the magnitude plot? Okay, now when you try to plot the magnitude plot, e power j omega t does not really play a role because it has magnitude 1. So if sigma is less than 0, we have this to be the magnitude plot. If sigma is greater than 0, then we have, okay, so this is sigma less than 0, this is sigma greater than 0. Now what about the phase plot? Now sigma does not play a role in the phase part because the phase is completely given by e power j omega t. And what happens to the phase as a function of time? So we have, if you compute the phase, what we have is just omega t. So omega t is only the phase because this portion is not complex, it's only the magnitude. This is the only portion and the phase is omega t. So as time changes, what happens to the phase? So clearly you can see that the phase is just a straight line, something like this. Okay, and the slope of the straight line is omega. So at t is equal to 0, you have 0. At t is equal to 1, the phase is omega. At t is equal to minus 1, the phase is minus omega, right? But then keep in mind, we said that when you compute tan inverse of any number, you will get only between minus pi to plus pi. So in fact, even though the line is actually a straight line from minus infinity to plus infinity, which is like this, when you compute it, you will get something which is phase wrapped. In other words, something like this. Which is as good as taking modulus with pi, right? Because it cannot, so any phase which that goes beyond pi will wrap around. So if it as you can see here, the phase value is actually going beyond pi. Okay, so it is going beyond pi, so it wraps around, comes on this side. So this is like saying anything, any theta plus n pi or 2n pi is the same as having the theta when you compute cos of theta or sine of theta, right? So that's exactly the reason why we have this phase to be wrapping around. Okay, so we have this wrapping around of phases from minus pi to plus pi because of this. This is pi, this is minus pi. So if you see a phase plot which looks like this, which is like a sawtooth wave, then actually it is just a straight line, okay, with whatever the slope is. In this case, the slope is given by the frequency omega. Okay, So the slope has to be omega, because remember, frequency is nothing but the rate of change of the phase. And the phase, if you take derivative of that, which is equivalent to the slope, must be equal to the frequency, and that in this case is omega, right? And it's a straight line with slope omega, but of course, because of this phase wrap, we will get the phase to be moving between minus pi and plus pi. Okay, so maybe we'll discuss a little more in detail what is this phase wrap, so that you understand what is going on. Now, if we plot the phase of e power j omega t, the angle of, let's say, e power j, what is the phase? Tan inverse of b by a, right? And what is tan inverse in this case? It is tan inverse of b by a, tan inverse of sine omega t by cos omega t, which is tan inverse of tan omega t, which is omega t, right? So for t is equal to 0, 0, and then so on, the same thing, right? So that is phase is equal to omega t. This is the function that you're plotting. So basically, you're plotting this function, which is nothing but this straight line where this is 0 and at t is equal to 1. This is omega, and t minus 1. This is minus 1. This is the phase plot. Okay. Now let us say this is pi and this is minus pi. So this is an absolutely correct phase plot, nothing wrong with this phase plot. But when you simulate it, let's say, and when you compute it in either MATLAB or Python or some simulation software, what you will see is tan inverse of some number here divided by some number here. And this number can always be only between minus pi to plus pi or 0 to 2 pi, whichever. Okay. So because it is between minus pi to plus pi, when you compute this in simulation and plot it, the values will be bounded above by this minus pi and plus pi. Okay. That means if I have to plot this, in this region, I'll get this straight line exactly as such. Great. But the moment I go out of this point, now I'll get here, let's say I'm trying to plot the phase at this particular point, then it is pi plus some, let's say, epsilon. But tan inverse of some theta is always going to be between minus pi to plus pi, right? So it cannot give a value which is greater than pi. So it will wrap around, meaning, so you start from this point, from here to here, the angle is pi, okay, and from here to here, the angle is minus pi. So what is pi plus epsilon? So pi plus epsilon is something you start from here and go here. This angle is pi plus epsilon. But then tan inverse is not going to give you anything that is greater than pi. So what it will give you is the other side. It will compute whatever is this angle. And what is this angle going to be? This angle is nothing but minus pi plus epsilon. Okay. So this gives the complete circle. So this is what tan inverse function will give you as the phase of this particular point. So whatever is at pi plus epsilon will end up coming at minus pi plus epsilon. Okay. So this function or this value will come here. Similarly, whatever is below this, so let's say something here is minus pi minus epsilon. So what is minus pi minus epsilon? So going back to this diagram, so minus pi minus epsilon will be somewhere here. This will be minus pi minus epsilon, which is as good as saying that it is equal to plus pi minus epsilon. Okay, and that is what we'll get here. So this point directly corresponds to this. This is what we'll call as phase wrapping. Okay, so this is what we'll observe as phase wrapping when you plot these functions in any simulation software. Let's try and plot the magnitude and phase plot of cos omega t. So if you try to plot the real and imaginary part, it's easy. Imaginary part is 0, nothing. So the real part is simply cos omega t, you'll get the sinusoid. So what if you plot the magnitude? Then you'll just get something like this on either sides, right? So it's easy. But what if you try to plot the phase plot? So if you try to plot the phase and then compute the phase at each and every point, you get tan inverse of the imaginary part divided by the real part. Imaginary part is 0. So does that mean the phase is always 0 here? One thing that we have to be careful is this signal can take negative values. So whenever the signal is positive, then the phase is 0. That is okay. But whenever the signal is negative, the phase is pi, right? So which means that the signal is having a phase of 0 whenever it is positive. So in this region, right, it is positive, and in this region it is negative. So it is actually pi. So the phase signal actually looks like a square wave for cos omega t. So you have to keep this in mind when you plot the magnitude and phase plots of real valued signals. So the real valued signals will always have a phase of either 0 or pi, essentially, which is telling the sign of the signal is either positive or negative. Okay, that's it. So whenever the signal is negative, the phase will take a value of pi. Whenever the signal is positive, the phase will take a value of 0. So this is how we have to plot the magnitude and phase plot of real valued signals. This we have to keep in mind. For complex valued signals, we just learned how to plot the magnitude and phases. Okay. So this tells us how to use complex valued signals, why they are important, and how to visualize them using these different kinds of plots. So once we have understood the representation of signals, then we can study more about the properties of the signals.